Welcome back to Physics 141 Online. I'd like to work out one final example in this part of the course that puts all the pieces together that we've been learning. The properties of ideal gases, the first law of thermodynamics, the definition of a heat engine and efficiency, and then the maximum possible efficiency that heat engines can have according to the second law of thermodynamics. So you can read the problem statement. N moles of a diatomic ideal gas initially at P1 and V1 are heated at constant volume to a pressure 3P1. After this, the gas expands to a volume 4V1 along a straight line on a PV diagram, where its pressure returns to P1. Finally, the gas is compressed isobarically to return to its initial state. Draw the cycle on a PV diagram, calculate its efficiency, and compare it to the maximum possible efficiency for a heat engine operating between these two temperature extremes. So let's draw the PV diagram here and then label it according to the different steps involved in this overall process. So we know that it starts at P1 V1 and then the pressure goes up to 3P1 and then it's going to expand. So that gives me a pretty good clue that I've got to start down here, and I'll label the volume V1, the pressure P1, and then we know it goes upward, directly upward to a pressure 3P1. And the scale is not important that it be perfect, but we should indicate that it goes directly upward, and the arrow tells us the direction that the process is operating. And so now from that point it's going to expand to a volume 4V1, which I'll label over here, and then it just tells us, it doesn't tell us it's a special kind of process, but it tells us that it moves along a straight line on a PV diagram. So it's going to end up out here, and I need to try to draw a straight line then if I can do this. That's not very good. Let's try again. Nice thing about this pad is I can erase something. Okay, that's a little bit better. So it expands out to a volume 4V1, and the arrow shows the direction again, and then it's compressed isobarically back to its initial state. So I'm going to label these because when I make my table it'll make it a little bit easier to come up with labels, appropriate labels for this. So let's assume that we can label the initial state A, and then it heats up to B and expands to C and returns to A. So once again, I'm going to make a table where we have a place for the steps, and then room for, actually I'm going to need a little more space here, room for the delta U, the heat, and then the work done for each of the steps. So let's put those in first. Delta U, Q, and then W. And so we're going to have the step A to B. Next would be B to C. And then finally C returning to A in order to complete the cycle. And remember that a working heat engine has to have that property. It's got to go around a closed cycle on a PV diagram. Okay, so we'll draw in some lines here to try to make this a little bit easier to read once we fill in all the pieces. And this will be important in calculating the efficiency, and it'll also just give us practice working through each of these steps. So we start at point A, and we know that in order to find the delta U, in order to find the change in the internal energy, we're going to use the equation for a diatomic gas. We know that U is 5/2 nRT, and so delta U is 5/2 nR delta T. So what we will need in order to calculate delta U is we're going to need to know the temperatures. And so from the ideal gas law, remember we've done this kind of a step before, TA then would be PA VA over NR. And so I can look on the diagram now and just read that off. So at point A, the pressure is P1, the volume is V1, and we'll just leave it in terms of those initial given quantities, P1, V1 over NR. So similarly, we can write down what TB and TC, what values they have. TB has got PBVB over NR. Well, PB is 3P1. So it's going to look just like TA did, except it's going to have 3P1. The volume is the same, V1 over NR. And so it's just 3 times what the initial temperature was at TA. And then TC, if we look at the pressure and the volume at point C, the pressure is back to P1, the volume is 4V1. So when I multiply those two, I'm going to get 4P1 V1, where the 4 came from the volume value over NR. Alright, so now I've got all 3 temperatures that I need, and I can start cranking out the changes in the internal energy for each of the steps. So I'll go through that pretty quickly. Delta UAB then is 5/2 NR from the equation above, and now we've got T final minus T initial. T final is TB, right? So that's 3P1 V1 over NR minus P1 V1 over NR. And what's nice here is that 3P1 over NR minus P1 V1 over NR gives me 2P1 V1 over NR, right? The 2 and this factor of 2 in the denominator are going to cancel, and the NRs are going to cancel as well. So when I multiply this all out and simplify it, I get 5P1 V1. Alright, that's kind of nice. Simple, so I can write that down, 5P1 V1 in my table for A to B. Now look at what else I can do directly for A to B. I know that that's an isovolumetric process. There's no change in volume, and therefore there's no work. So right away I can fill in the first line on the diagram, because remember that delta U, I'll just write down the first law because we'll come back and use it later. Delta U is Q plus W, and for a process where W is equal to 0, then Q and delta U are the same. So I've already made pretty significant progress on this. Now let's do B to C. So delta U, B to C can be done in the same way we did for A to B. Now we've got the 5/2, we've got the NR again. Now we look at the temperature at C for P1 V1 over NR minus temperature at B is 3 P1 V1 over NR, and so this simplifies. The 4P1 V1 minus 3P1 V1 is just P1 V1. The NRs will cancel again, and so this will give us 5/2 P1 V1. So I can write that down, 5/2 P1 V1. I'll get to the work in just a minute, but I might as well finish the delta U calculations while I'm on a roll here. Delta U CA, again we'll have our 5/2 NR, and let's see, TA is the final temperature. That's the P1 V1 over NR minus TC, which is the 4 P1 V1 over NR. And so in parentheses I'm going to have a negative 3P1 V1, so this will give me a negative 15/2 P1 V1. Note that it's negative and makes sense because the temperature clearly is going down. When you go from C to A, you're getting closer to the origin, and we know from the ideal gas law that that means the temperature is lower. And so a negative value should not surprise us. We should really expect to have that in a step like this. So negative 15 halves, P1, V1. And now all that remains in order to fill out the table is to find the work for B to C and the work for C to A. And if we look at B to C, we know that that's an expansion process. So work BC should be negative, right? Because remember, work is defined so that when something does work on the gas, it squeezes it, it compresses it, that's positive work. So WBC we know should be negative, and the easiest way to find it is just to find the area under the curve from B to C, which is going to run all the way down to the volume axis. So I've got basically the area of the triangle, and then I've got the area of the rectangle underneath it. So I'll calculate those areas using my simple formulas for area of regular shapes, and then put a minus sign in front of it. And so that what that means is then WBC is the negative of the sum of these two areas. And so first of all, the area of the triangle, well, that's 1/2. The base of the triangle goes from 4V1 to V1, so that's 3V1. 3V1. The height goes from P1 to 3P1, so that's 2P1. Alright, so that's the area of the triangle part. And then there's the rectangle underneath it, which goes at P1, right? It's the area right here. I'll just put some dotted lines in, and that's what we're trying to find. This area here. And that's pretty easy, so it's just the base times the height. The base is 4V1 minus V1, so that's 3V1, and the height is just P1. So those two terms added together give me the two areas, and I'll shade in the triangle area there, 2, to indicate what I'm doing. So we find that the first term is going to be 3P1V1. The second term is also 3P1V1. And that means that we're going to get negative 6P1V1. Alright, so we've got that. We can put that in for B to C, negative 6P1V1. Alright, and we'll get the heat in just a minute. Let's finish the work. Now work C to A. Here, for work from C to A, we should expect this to be positive, right? Because it involves a compression. And so, we know work C to A will just then be the area under the curve from C to A. And we've actually already calculated that, but because that was part of the work for BC, only now it's going to be positive work. So WCA will be 3V1, which is the base, times P1, which is the height. That's it. All right. So we can write that down as well, and that's 3P1V1. And notice what happens here. There's no work done going from A to B. From B to C, the gas expands, which means it's doing work on its environment. And because of the way we defined work, that tells us that the work term is negative. So that much work is being done in the environment, but then to return the gas to its original state at point A, we have to compress it. And so it actually then requires work to compress it. But the sum of those two is going to be the net work that the gas actually does on its environment. And it turns out that that is the area of the triangle. Okay, and we'll get to that in just a minute when we calculate the net work. So that takes care of the work. Now finally we can get the Q. We go back to the first law. Q then is delta U minus W, right? So we've already done that for AB. So QBC is delta U BC minus WBC. Delta UBC is 5/2 P1V1. Now here we're subtracting the negative, right? Minus a negative 6. So I'll just put plus 6 P1V1, and to simplify that just a little bit, 6 is 12 halves, so 12 plus 5 is 17. So we have 17 halves P1 V1, which of course we could write as 8.5, but I'll just put the fraction in here, 17 halves P1 V1. And finally, what's left is just to find the heat that's absorbed in C to A. Notice that in BC, heat comes in. The gas is absorbing heat at the same time that it's expanding to do work. So finally, QCA is delta U CA minus W CA. Here we're subtracting a positive number, so delta U is negative 15 halves P1 V1 minus 3 P1 V1, and so 3 is 6 halves. 6 plus 15 is 21, so negative 21 halves P1 V1. Alright, we filled out the entire chart. Negative 21 halves P1 V1. And notice that that minus sign means that the gas is releasing heat to its environment as it's being compressed. So heat comes in two steps. When you go from A to B, the gas absorbs heat. When you go from B to C, the gas absorbs some more heat and transforming some of that into work. Then to go from C to A, it has to release some heat. And we've already seen in class that that's characteristic of heat engines in general, that they absorb heat, they use some of it to do work, and then there's waste heat that's expelled to the environment. So all that's left for us to do is to calculate the efficiency and then compare it to the maximum possible efficiency that an engine operating between these two temperatures could have achieved. All right. So we'll get to see how efficient this heat engine is compared to the best that you could possibly do. So the efficiency, of course, you remember the definition, it's the net work that's done by the engine. So we say W net, but it's the work done by the engine. And in this definition, the work done is always assumed to be positive, even though in an expansion, when the gas is doing work on its environment, the W in the first law is treated as negative. When we calculate the efficiency, we just take the magnitudes. But then the denominator is important because that is the heat absorbed by the gas. Okay, it's not the sum of all the heats because only two of those terms are absorption terms. One is a release. So what we use is we look at the work done, and the work is the net work. And so it's the sum of all of those work terms, which turns out, as I mentioned before, in this case, to be the area of the triangle. When you have a closed cycle, it's the area enclosed by the cycle that turns out to be the useful work, the net work. And so when we add those two together, we get negative 6 plus 3, or negative 3 P1 V1, but I'm just going to write this down as 3 P1 V1 because we only care about the magnitude of it. Alright, now the heat absorbed is the sum of all the positive heat terms because heat was absorbed by the gas when it went from A to B and then also when it went from B to C. So the sum of those two is the total amount of heat that was available to the gas to do work. So that's 5 P1 V1 plus 17 halves P1 V1. And you see we don't even need values for P1 and V1 because when we factor it out of both terms in the denominator, it's going to cancel with the numerator. And so what we get in this case, when we simplify this, is a fraction 2/9 or 22% if we express it as a percentage. And so that is the answer that we're looking for that characterizes the efficiency of this engine. Now, what's E max? What's the maximum? And well, this invokes the Carnot efficiency formula, right? Carnot efficiency, if we look in chapter ch19 in the book, it tells us that if you have a heat engine operating between two temperature reservoirs, one at a high temperature, one at a low temperature, that the maximum possible efficiency for the Carnot cycle, the maximum efficiency that the second law of thermodynamics permits, is given by this formula. So what we need in our problem, we actually had three temperatures involved with this gas, but we just look for the highest and the lowest to plug into here. And so if we go back, we see that if I scroll back up for a second, we see that the highest temperature was 4 P1V1 over Nr. The lowest temperature was P1V1 over Nr. And so I'll see if I can squeeze this in here. So the numerator was 4 P1V1 over Nr. The second term was P1V1 over Nr. And the denominator was the 4 P1V1 over Nr. And I'm just going to put a slash here over Nr, like that. So the numerator, you're going to get 4 minus 1, or 3. The denominator has the 4, right? And then the Nr and the P1V1 terms cancel out. So what we find with this is that we get 3 over 4, 3/4, or 75% is the efficiency of the maximum efficiency heat engine that we could have had operating between these two temperatures. Alright, so sorry that's kind of squeezed in, but you can see the conclusion that we draw is, first of all, we know that the efficiency of a real heat engine will always be less than or equal to this maximum efficiency, and here we can see it's quite a bit less, like 22% compared to 75%. So this thermodynamic cycle is not a very efficient cycle to use to make a heat engine, but it is a possible cycle, and I hope this problem then helps put together everything that we've been working on the last week or 10 days. Again, just to review, we're looking at the ideal gas law. We use that. We're looking at the first law of thermodynamics. We also then calculated work for the various processes, and finally calculated the efficiency and compared that to the Carnot efficiency for this heat engine. That should be helpful as you do homework problems and prepare for the final, and I will see you in class.